Hey guys, this is 8.1 through 8.4, and one thing we want to talk a little bit about before we get too far into it is a little bit of preemptively understanding. So right here I've got a bicycle wheel, and we understand that things rotate and they spin, but we also need to recognize that there is dynamics that happen here. For instance, when the wheel is spinning, we might ask questions like, how fast is it spinning? And how do we measure how fast something's spinning? We could talk about the degrees that it rotates through. We could talk about how many revolutions it rotates through given a specific amount of time. That similar concept, that should feel very similar to the concept of velocity or distance traveled over time. We might also worry about things like, does the speed of the wheel increase at all? Does it start to go faster and faster? Is there an acceleration to the rate at which it spins? And that includes slowing it down. And then, direction. Which direction is it rotating? How many rotations does it go through? Those are all questions that we might want to ask. And you might think, well, it's just a spinning wheel. Why does that matter? Eventually, we're going to get into concepts of angular momentum. We talked in Chapter 7 about momentum and how things travel in a direction. And the bigger momentum they have, the more they're likely to overpower others and impact others with that momentum. Same thing can be said for angular momentum. If we take this bike wheel, and we've all seen a bike before, when you're not pedaling, you're not doing anything, the bike wheel falls over, and there's nothing fancy about it. However, if we give the wheel an angular momentum, that angular momentum will need to be conserved. It doesn't want to stop rotating in the same way that it is. And while there are forces, or what we call torques, that will be applied to it, the wheel will want to stay upright. Now it's doing what's called gyroscopic precession. We can talk more about that in a future video or future class time, but today we just want to acknowledge that angular momentum is a very, very powerful thing. And it allows us to make some discoveries and some interpretations of information that are very, very useful to us. So we need to go through the book and talk about a few simple things. You'll see here in a minute, I will have changed the homework assignment, so make sure you look real closely at that. This lab day that we would normally have on Wednesday, it's going to kind of be a scrap day unless we go back to green, just because we don't have the time I can't do a lab if you're not into the school. We'll try to do some things remotely, but depending on whether you're in class or you're out of class, that'll make a difference. All right, so let's jump into the book and go to chapter 8. All right. Beginning with the beginning. All right, we've got angular quantities. All right, so obviously we know things rotate. That's not too crazy for us to understand. But we do want to understand a couple of things that are specific. For instance, a radian, we should know, is the length that something rotates at one radius along the circumference. That there are 2 pi radians in 360 degrees. Sorry, I had to burp. Okay, let's start that over. All right, so we have that 360 degrees is the same as 2 pi radians. Okay, one other term you'll see using here will also be 1 revolution. Okay, you'll see that revolution or rotation per minute, and these 3 things are interchangeable for that. And so if we talk about a bike wheel going through 4.5 revolutions, and we want to know how many radians it rotated through, we just take 2 pi times that 4.5. It's a pretty easy calculation to make when we're going from revolutions to radians or radians to revolutions. Let's see, what else do we need to know? All right, so we're going to jump way down here because there are some very specific things that we should already understand. For instance, in our kinematics, in our straight linear kinematics, x was our displacement. The wheel's not necessarily, we can still talk about its movement side to side as it rolls across the ground. But when we talk about the angular piece, we're really wondering how far it rotates around. And so in our formulas, whenever we used x before, we're going to be able to change that to theta. Okay? And x, the distance traveled, will equal the radius times the number of radians that we rotate through. Okay? So this is a formula that calculates the relationship between moving across the ground and how much rotation took place. Velocity. We know a lot about velocity. We have what's called angular velocity, or speed or rate at which it rotates. We use the Greek letter omega, little w. It's a funny looking W. Don't make it just a regular W. It should be like a loop-de-loop W. That was a really crappy job of writing that, Mr. Welch. There you go, a loop-de-loop W. And the relationship between moving across the page and spinning in a circle, if there's no slipping, would be that the velocity across the page equals the radius times the angular velocity. So again, connection there. And then we have what's called a tangential acceleration. That means that the velocity at which we rotate, the angular velocity, is going to accelerate. It's important that we understand, of course, there has to be an inward, oops, that's a really bad job of inward. There has to be an inward acceleration to create the circular motion. Sorry. So then that leads us to dealing with the tangential acceleration, the acceleration that causes it to spin faster or spin slower, called a tan. That will equal alpha, okay, the Greek letter alpha, and the tangential acceleration, the amount it accelerates and its velocity as it spins, its angular velocity, will equal the radius times alpha. So we have these conversions from straight line motion to angular or rotational motion, okay, and that leads us to a couple of things. One, we have this definition called a frequency, and then a definition called the period. Okay, so these are two different things. They are multiplicative inverses of each other. They're the reciprocals of one another. So if we say that it takes, the period is how long it takes for one rotation. So if the period equals 2 seconds, okay, then the frequency will equal 1/2, and we use the unit hertz, which is per second. So it does 1/2 of a rotation every second because it takes 2 seconds to complete the whole rotation. So this relationship between those two things is closely linked, and we end up with this formula here, that the angular velocity, how fast it's actually spinning, is equal to 2 pi times the frequency again being measured in hertz. So we have these different definitions, period and frequency, and they're going to get used interchangeably. Oftentimes we really want to talk about frequency, but when we talk about things like the Earth moving around the sun, we'll often talk about not its frequency, but its period or periodic motion. And so sometimes we use those words to talk about one thing versus another. I don't really want to know how much of a rotation the Earth makes per day around the sun, or revolution rather, but I do maybe want to talk about its period, how long it takes for it to get around the sun. So there are times when we might talk about one versus the other. But here's what we're really after. We have our kinematics. These are the kinematics of linear equations, and we get to use the exact same thing in terms of angular. A couple of things that we have to keep in mind, okay? We don't want to use, whatever unit we're using, we're going to have to live with that unit. I'm a big believer in turning all of these into radians per second or radians per second squared. Some people like to use revolutions. Radians is our measurement for angle of rotation, so let's just go that way. So you might have to make some conversions from time to time. You'll get RPM, revolutions per minute, quite often. We want to convert those into radians per second, which if you just take those two units, a revolution per minute, to get rid of a revolution, you have to times by something to get into radians. And so one revolution is 2 pi radians. And then to get minutes to seconds, 1 minute is 60 seconds. So you would be taking whatever, say it's 3 revolutions per minute, 3 RPM, you times by 2 pi and divide by 60. That's how you'd get your calculation in radians per second. We keep cruising down. when there's no slipping, and this is something we talked about earlier, the velocity of an object across the ground, if we say about its translational velocity, will be equal to the radius times its angular velocity. Okay? If it's slipping, obviously it's going to spin more than it moves forward, and so that makes a big difference. All right, I think the last thing we need to cover in this unit is what we call torque. Torque is a force being applied at a distance from the point of rotation. Okay, you can think about this with pipes and wrenches and different things like that. It's called a lever or a lever arm. We use it for leverage. And what we find is that the more torque we apply, the more the object will accelerate. Okay, and so we end up with this formula right here. If we want to know how much torque is applied, it will equal the radius of rotation times the force applied times the sine of the angle between those two vectors. In other words, in this torque symbol, you often write it like that. So it's Greek letter tau. Okay, if I have a force and I'm going to apply my force, and then I compare that to the radius, which is this direction, okay, from there to there, the angle between them is going to affect how much torque I actually am applying to the object that I'm trying to rotate. It's unit, okay, for torque, okay, when you take meters times forces, that'd be meter newtons. Okay, so we have meter dot newtons, meters times newtons. Newtons times meters, okay, force times distance is also something we would use to calculate energy or work, and we want to make sure that we distinguish this is not an energy calculation, and so it's really important that we put meter newtons. You may have heard of foot pounds before, and that can kind of align why we put meters then newtons to follow along with that. I think that's where we're going to stop. You should be able to do some kinematic problems in Chapter 8 based on what we did so far. Using those kinematic formulas, you should be able to answer a few of these questions to start the assignment down here. For instance, question number 4, blades of a blender rotate at 6,500 RPM. When the motor is turned off, the blades slow to rest in 3 seconds. So that's time is 3. You have an initial angular velocity, that'd be an omega naught. Your final velocity would be 0, and we're looking for the angular acceleration. So questions like number 4, it's literally omega equals omega naught plus alpha t. We know omega is 0. We want to go to 0. We should have the omega naught, whatever this 6,500 RPMs is, in radians per second. Alpha is what we're looking for, and time is 3 seconds. These are the same things that we calculated before. The difference is that they're angular velocities and angular measurements. So I'm going to leave you to work on those. I really do believe you guys can manage them. If you have questions, please talk to me, and I'll try to help you out the best I can. Good luck, and we'll see you in class.